So we can think about this in terms of moles or molecules, and maybe molecules will give us an idea, of course, why it's limiting. We see that if we're going to combust carbon or methane, CH4, with oxygen, it takes 2 molecules of oxygen to react with 1 molecule of carbon. Okay, because with the carbon, 2 of those oxygens are going to form a bonds with that carbon atom, leaving 4 hydrogens. Okay, if it was just 1 oxygen, we'd have 4 hydrogens left over, nowhere to go. So of course we need an additional oxygen atom to form the 2 molecules of water. So if we have 5 molecules of methane and 8 molecules of oxygen, which one is going to run out first? Which one is going to be our limiting reactant? Okay, so what we can do is set up conversion factors just like we did previously. Okay, and so if we have 5 molecules of methane, we know that it takes, for every 1 molecule of methane, it's going to take to produce 1 mole of CO2 or 2 moles of water. Since we have 2 products here, we can select either for us to determine our limiting reactant. Okay, but the trick is you have to use the same product for both of your calculations. Okay, so let's calculate how many molecules of carbon dioxide we can produce. Okay, we can see that for every 1 molecule of methane, we're going to produce 1 molecule of CO2. Molecules of methane are going to cancel out. And so with 5 molecules of methane, we can produce 5 molecules of carbon dioxide. Now we do that same calculation with our 8 molecules of oxygen, and we will quickly realize which one is going to run out. So if we have 8 molecules of oxygen, we can see that for every 2 molecules of oxygen, we're going to make 1 molecule of CO2. And that gives us 2 molecules molecules of oxygen that cancel out. And so that gives us 4 molecules of CO2. Okay, so it turns out that after we make 4 molecules of CO2, we are going to run out of oxygen, so there's no way we can make 5 molecules of CO2. We just don't have enough oxygen. So oxygen is our limiting reagent, or limiting reactant. And of course that means methane is our excess reactant. Okay, now so far all of our calculations we've done is on paper. It turns out that there's a big distinction between what you can theoretically make and what you actually go into lab and make. Okay, if we go back to our pizza example, all of these ingredients tell us that we can make 3 pizzas. Okay, so theoretically we can make 3 pizzas, but what happens if we accidentally leave one in the oven too long? We burnt 1 pizza. That means we actually only made 2 pizzas. So we theoretically could have made 3 pizzas, but we actually only made 2. So that is the big distinction between actual yield and theoretical yield, and of course that is a useful. Those are useful terms for chemistry. We can calculate how many moles of a product we can make, and that's our theoretical yield. But of course that may not be the case. And as you can see with the pizzas, the theoretical yield is always determined by the limiting reagent. So here we have another example. Let's say we have 1 mole of silicon and 1 mole of nitrogen that react to produce trisilicon tetranitride. Okay, we can see the stoichiometry here. 3 moles of silicon produce 1 mole of product. 2 moles of nitrogen produce 1 mole of product. So what happens if we have 1 mole of nitrogen and 1.2 moles of silicon? What is our theoretical yield? How much product can we make? Okay, so we just take our number of each of the reactants our 1.20 moles of silicon and figure out how much product we can make. Well, we know that if we have 3 moles of silicon, we can make 1 mole of product. And so that will give us 0.40 moles of products, trisilicon tetranitride. Okay. Well, how many moles of product can we make with the 1.00 moles of nitrogen we had? Okay. Well, we just go back to the coefficients and figure out the stoichiometry there. In this case, 1 mole of product is produced for every 2 moles of nitrogen that we had. And so that will give us a value of 0.50 moles of product. So our lowest value, it will always be our theoretical yield. Once we make 0.4 moles of product, we're going to run out of silicon, and therefore nitrogen is in excess. So our theoretical yield is 0.40 moles of silicon or trisilicon tetranitride. Again, based on our limiting reactant. Okay, so as I said, that's our theoretical yield, but of course, due to a variety of experimental conditions, we're probably not going to be able to make our theoretical yield. We're going to produce somewhat less than that, and that is referred to our actual yield. So, a very convenient way to illustrate our relationship between actual yield and theoretical yield is to calculate our percent yield. We do that by dividing the theoretical yield from our actual yield and multiplying by 100%. Because if you say you made 10 kilograms of product or 1 gram of product, that really doesn't have, can't really compare how efficient the reactions are if you don't know how much you started with. If you made 1 gram of product and your theoretical yield was 1.1 grams of product, that's a pretty good efficiency. If you made 10 kilograms of product, but you had enough starting material to make 100 kilograms of product, it's not efficient. So a better way to illustrate those relationships is through percent yield. Okay, so let's do an example of that. Here we have production of titanium from titanium 4 oxide with carbon. Okay, if we start out with 28.6 kilograms of carbon and 88.2 kilograms of titanium oxide, we go into the lab with that amount of material and we actually produced 42.8 kilograms of titanium. So whenever you see obtained or produced, actually produced, that's referring to your actual yield. That's what the chemists went in the lab and did. Okay, so with this information, we can find the limiting reactant, the theoretical yield, which again will be based on our limiting reactant. And since we know the actual yield, we can calculate the percent yield. Okay, so again, if we want to find the limiting reagent, we need to calculate how much product we can make. All right, so let's just start out with 28.6 kilograms of carbon. And we're going to calculate how much product we can make. Now again, since we have 2 products, it doesn't matter which one we go after, but since we're going to be going back to the amount of titanium to calculate our percent yield, it makes sense to calculate amount of product in titanium. Okay, since we're going to have to go to a molar ratio, not based on or from mass. Of course, our molar masses are in grams, so we're going to convert these to kilograms. So we know that in 1 kilogram, we've got 10 to the 3rd grams. And if this is carbon, we're going to convert to moles. So in 1 mole of carbon, we've got 12.011 grams of carbon. Again, just from our periodic table. And our balanced chemical equation tells us that if we have 2 moles of carbon, we're going to produce 1 mole of titanium. So there's our relationship there. 2 moles of carbon will produce 1 mole of titanium. Okay, moles of carbon cancel out, grams of carbon cancel out, kilograms cancel out, and so if we do this in our calculator, this is going to give us 1.19 times 10 to the third moles of titanium. Okay, we're going to need to do that same calculation, but with our other reactant, TiO2, titanium fluoroxide. Okay, this time we're going to start with 88.2 kilograms of TiO2. Again, we're going to need to calculate, we're going to convert that to grams. So 10 to the third grams and 1 kilogram. We need to calculate the molar mass of TiO2. So if you do that, you'll find that in 1 mole of TiO2, you've got 79.88 grams of TiO2. And then we can go to look to our balanced chemical equation and realize that 1 mole of titanium oxide will produce 1 mole of titanium. And so moles of titanium oxide cancel out, grams cancel out, kilograms cancel out. And this will give us 1.10 times 10 to the third moles of titanium. Okay, so which is our limiting reactant? That's always going to produce the smallest amount. Our smallest amount is 1.10 times 10 to the third moles of titanium. Once we make that amount of moles of titanium, we're going to run out of titanium oxide, TiO2, titanium fluoroxide. So that is our limiting reactant, TiO2. This really is our theoretical yield in moles. So that's our theoretical yield in moles. Of course, because we've got our actual yield in kilograms, we're going to convert that to kilograms. But theoretical yield just refers to the amount. So that's fine to report it in theoretical yield in moles unless it asks for something else. Okay, but our last calculation we need to do is calculate the percent yield. So our percent yield is equal to our actual yield over our theoretical yield times 100%. Okay, so we know that our actual yield is 42.8 kilograms of titanium. We're going to need to multiply it by 100%. But our theoretical yield we just calculated was in moles, so we need to convert that to kilograms. Because when we use percentage, it doesn't matter what our units are, they just have to be the same. So conversely, we could have converted 42.8 kilograms to moles. So that there is 1.10 times 10 to the third moles of titanium. That was our theoretical yield. And there are 47.88 grams of titanium in 1 mole of titanium. And so, to put it in kilograms, we can say that there's 1,000 grams in 1 kilogram. And grams are going to cancel out, moles of titanium are going to cancel out, and that will give us a value of 52.7 kilograms of titanium. And so that is our theoretical yield in kilograms. And so we'll just put that in this value, 52.7 kilograms of titanium. Kilograms of titanium are going to cancel out, so we're going to be left with units of percentage. So our percent yield is equal to 42.8 divided by 52.7 times 100%, 81.2%.